last time, if I'm not mistaken, we had done a single soil going below a sheet pile wall, and we were going to start doing the same thing, but this time with three soil profiles, two soil materials really, but with three soil sections. So out of curiosity, I know we had finished suggesting that maybe some of you wanted to try it. Did anybody try it?
Seriously, no.
Okay. That's how you you figure out if you got really the juice of the lesson. So I can only recommend you try such little things. So let's see what the materials are. So we basically have the three soils. Okay, and we wanted to let me see. So we were at we had defined kx and ky, correct? So that's where we were at. Oh yes, and we had made a little image here. That was our initial, based on our initial interpolation. That's for one soil material. And we had also seen how to set it so we can use this. I'm not sure. Oh, here we just have some random numbers. Okay, I think we can delete sheet 2. Correct. Yeah. Okay, and sheet 1, did we have? X squared. I think this was also for some examples on how to define ranges, correct? If I'm not mistaken. Okay, let's delete that. Single soil analysis. And now we can basically, let's copy this. Create a copy. And we will call it multi-soil analysis. Oops. Oh, that was my attempt at, oh, okay, let's delete this. Okay. And here obviously we had material properties. And of course we don't need this in material properties. Or this, because the only thing that we are concerned about here. So kx and ky. So for kx, we would find the averages. We were saying. Okay, and we had so kx and ky's that were defined. One was short on the one had the same number of columns as the number of nodes, and the other one had the same number of rows, right? So Just
Excuse me, I have one
yes,
question. Uh, in this example, why didn't you define the boundary conditions like previous example? You added some rule left and right side of.
because this is not this analysis yet. This is just the material properties.
Oh, okay.
Okay, we are going to do the analysis on this page. Sorry, I'm gonna rename it multi soil analysis. Okay, so we don't need boundary conditions when we're defining here the hydraulic conductivity. So I have kx equal ky in this particular example, but just remember it doesn't need to be the case. Okay. Um, in the case of kx, so let's examine again. So notice that here we have one row less than we have nodes, right? And in the case of ky, we have one column less than we have nodes. Okay, so let's go back because that's where we had left, I think, last time. And so so if we have a series of nodes, that represent our domain, right? So in this particular case we have, okay, so the materials, so let's represent also the lines that join them. Oops. Okay, so we have our little nodes here on our grid. However, as it happened, um, so as it happened, we have our the material properties are associated with the soil, so with the material in between, right? So the material properties belong to the materials that are in between, not at the nodes. Okay, so if water has to go, so it suffers a head loss because of the hydraulic conductivity or resistivity, which is the inverse of conductivity. So water that goes from here to here loses, or sorry, from this node or from here to here loses head because of the resistivity of the soil that's there, right? So that means that it's the material in between that matters, not whatever I find at the nodes. So if I have my rows 0, 1, 2, here I have my columns 0, 1, 2, 3, 4. Okay. Now let's say that we have to consider kx. Kx, I want to calculate kx for this node, like when I want to calculate the head at that node looking at the neighbors. So I have to look at the two neighboring nodes, which are this one and that one, correct? So where should I calculate the hydraulic conductivity? Well, for Kx, I have to calculate the hydraulic conductivity at the edge of two elements, which could be two different materials, right? This material and this material could be different. So what I have to do is do the average of these two elements and find it on the Kx. So I find for this node that one, that one, that one, and that one. And I do that one, 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 that one. So for this one, I have these two, etc., etc., etc. So in theory, for Kx, Ky. Just a sec. I'm just making sure that I have the same reasoning as last time. So I have to find Kx based on the neighboring values, and when I do Ky, on the other hand, so I look at this. So if I look at, that cursor is hard to find. Where is my cursor? Okay, so for this node here, right, I need to look at the average between these two cells. Let's change the color. I think it's a bad color for that particular. This one maybe. Okay. So for this node, I have to look Ky here and Ky there, right? And so I should have Ky, 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 and Ky, correct? So again, Ky there, Ky there, Ky. Okay. So for Ky, I have the number of rows minus 1, and for Kx, I have the same number of rows. So for Kx, I have a number of rows and number of columns minus 1. And for Ky, we have number of columns, same number of columns as the nodes. Correct? That's how it's supposed to go. Let's make sure we have that correctly here. I think I have mislabeled the sheets, right? Because this one is average. This one is actually Kx, right? It's the average of the two lateral neighbors. So that's actually Kx. Yeah, Kx. And this one will be Ky. Because I'm averaging, I'm averaging in the vertical direction, but in this case it's the average of constants, so it doesn't really make a difference, right? If I average 0.5 times that plus that, oops.
Excuse me, we don't see the.
Oh, sorry, I forgot to change. Okay, so we have n4 plus n6, right? So that can be the average as much as I want. I keep a nice straight boundary because ky, so ky has one less row, kx has one less column as the number of nodes that I have in my domain. Okay, and the reason for that is as we represented in this view here, where we had one less because we do the average of the neighbors in one direction specifically. So we have to keep that in mind when we're doing the multi-soil analysis in that case. So what was again the multi-soil analysis that we had established for our problem? So let's go back. We could redo it all again, or we could just go to the what we had last time and see that it's basically a weighted average where the values of the delta x and delta y are also multiplied. In this case, our delta x is equal to delta y and both are constant. So we could just, for this particular case only, okay, we can just assume that we have a value of 1 everywhere. So we can just say 1, 1, 1, and 1, right? And because of that, we can disregard it because delta x equals delta y. If delta x is different than delta y, then we have to go back to this. But what we have to consider is here that, so we have the weighted average basically of the delta x. So we have the k of neighboring times h of the neighboring values, and then we make that sum and we divide by the sum of k's of the neighbors. Okay, so let's see if we can do that correctly. Based on what we had previously established. Now, I don't remember what we had here. In terms of, okay, we have defined dx. Oh, dx and dy are different, so I'm sorry. We cannot, in this particular case, ignore dx and dy because we did use different values, so we would get a higher resolution. So we have to go to the full definition, but fortunately dx and dy, so delta y squared is multiplied by the with the x differences, the kx's, okay, and the delta x goes with the ky's, okay. So that's an important little touch to remember in this particular case. So let's go into our multi-soil analysis. Oops, that is defined. So let's go to our multi-soil analysis. Okay, so we can zoom into this and change a little bit our calculations. Again, here we're using the ability of the spreadsheet to to iterate calculations, and so we will have to keep using them until we're done. So we have, we do have delta y, but in this case, okay, we have E5 plus, so delta y, so this has to be the neighboring cells, right? So in this case, what did we have for E5? Oh, it's a hidden column. That's why we're not seeing it. Oh, or it's just beyond. Okay, we're not at the edge. Okay, so this one is as before. The boundary condition have not changed, so that remains as is. And this is a general formula. And so we have to change. So it's we have to go into kx here. So kx of the neighbor, so we go to kx's, and the kx's will have one less column, correct? So we go to the kx's, which do have one, oops, how come we have the same number of columns here? Let me make sure that I have everything correct. Oh, oops. Is this? Oh. Oh, we skipped. So, they were correctly labeled then. Kx has one less column. I'm sorry, it's my bad. No, wait. I just want to make sure that I didn't make a mistake here. Okay, so Kx is the average Okay, so if we look here, so for all of kx's, we take, so these are the kx's, and the kx's are based on the average, the vertical average of kx's, and there's one less column. Okay, so kx should have one less column and should be, so this was indeed kx because it's the vertical average. So I just made a mistake before. I went too fast. I did it correctly last week. What misled me was the number of rows because we were missing something at the top there. So we have k, this is kx, and this one will be ky's. Because the ky's are, wrong sheet. And this one will be ky's. Alright. Okay, so we have kx okay, so kx must be based on the average of the vertical neighbors. Okay, Okay, so here we make sure that we are the average of the vertical neighbors. This one is, oops, 5 times yeah, per the vertical. Okay, that's for kx. Did I not paste properly? Okay. Okay. It should still stay at that value, right? 0.5 times 5 plus 5. I don't understand why I'm getting 0. Can someone spot a mistake that I might be making here? 0.5 times the neighbor value should be 0.5 times 5 plus 5 should be 5. No? Yes. So 0.5 times this one, which is 5, plus this one, which is 5. I failed to see how I'm getting 0 there. This one is giving me a correct value. Let's see if it has to do with conditional formatting. Can someone spot a mistake there, or is it just a random weird oh, it was apparently a random weird behavior. Okay, it seems to have been a rendering issue. I want to paste only formulas. I want to paste formulas. Yeah. Okay, let's try moving again. Last time it was because of rendering. Oh. Maybe because the numbers are not, we have to go to allow iterations. Options. Formulas. Enable iterative calculations. Okay, that was it. Okay, so that one worked. That was correct for Ka, so we go from 0 to 9.5 because we're skipping. It's not really, it's 0.025 to, so those should really be in between, if you get my drift. So, and the for ky, for ky, again, so to recapitulate, for ky, we should have, so ky are the oranges, so we should have the same number of columns, and we're averaging horizontally the neighbors. Okay, averaging horizontally, and we should have one less row. And to keep things consistent with how they were in the other one, we're just moving this up by one. I'm sorry. Okay. And so this one is the neighbor. Okay, these two neighbors. So that's perfect. So we do have a transition here because that is ky, and we have neighboring. So little neighbors. Now, we have dy squared times, and now we have to go, this is dy, so we multiply by kx's, right? And kx's, as we said, have the same number of, kx have the same number of rows, but one less column. Again, I need to make sure that we have it correct. Yes. Okay. So we are considering kx. Kx for this row. Oops. So we are row at 1, and because we have the same number of rows as we have nodes, so we take, wait, is this d4? This is at 1. Oh, I didn't have a row 0 even here. Okay, that's a mistake in my calculation. Sorry about that. This. Oh, these are files. Okay, they're just invisible. That's what had me confused. It comes from the conditional formatting, I believe. Manage rules. Number. Okay, let's make it general. Okay. I don't know, does someone remember why did we do it intentionally, or we just had this accident as a random happenstance that this was formatted to make the numbers disappear there? So number general, it seems to have been intentional, but I don't remember why. Okay, so those are our boundary conditions. So we have to start here with the formula. Yes, okay, that's the first formula. And so we have to start here. Okay, so that goes to kx that was averaged for the upper one. Okay. And the next one, so we go to D and E. Okay, so this one, we look at the previous material. Oh, in this case, actually, because we're looking at the kx's from the neighbors, that should be 4. Okay, so at 4, at 4. Okay, so again, so kx's, they're these values here, right? So if I'm starting with my nodal one, it's going to be a special case in which I should have the same k as on the next one, right? So indeed, you might be right that for this we might want to have a kind of an equivalent to boundary conditions, in the sense that here we can say that's equal to the next one rather than the next. So this one are outside our materials, but technically
We can't see the.
sorry, but technically they are the. Okay, so here we just put the equation for. It's a little bit slow running on the VMware. Okay, so we just say that this one is equal to the direct neighbor. Okay, it's a bit boundary different from the boundary conditions that we have here. Okay, which refer to next over, and that's because right now what we are really doing is the so the lines in this case are material properties are in the lines between these cells. Okay, so that's why they're the next lines. So let me redo it for this term here. So kx, let's make sure that we got the correct value there. So we go to kx, and we're at a depth of 0.5. Sorry. So we are at 0.5. We're at the depth of 0.5. And so we go at D4. Was it C and D? It's C and D. So C4 and D4. C4 and KX and D4. So in the case of the node, we go from C to E, but in the case of the hydraulic conductivity, we go from C to D. Oops. D4. po. KXD4. Yeah, so that's the problem when we get neighbors like this, and things depend on calculation based on neighbors. Okay, once you get an error, it tends to propagate, unfortunately. So what I should do is basically I'm having a little trouble interacting with the software. I'm wondering if it has crashed. Yes, it has. Oh, it's back. Okay. It's very, very slow. Okay. So now we have we've done just the first term. We have to do the same thing for dx squared, so this multiplies by the ky. So ky, we are again at the same neighbors. So looking back to ky, okay, ky in terms of neighbors at the boundaries, at the top boundary, well, we don't really care. But the bottom boundary, okay, will not be part of the evaluation. It's extremely slow. I'm not sure why.
It's lagging a lot, Professor.
Oh, it's lagging a lot? No, probably that's the reason.
Your voice is also interrupted.
Okay. So here we can set it equal to... Okay, let me try something. Let's see if I can fix the lag. Let's avoid this altogether. Can I save? Let's save the file. Is it lagging less now? Okay, so if it's lagging less, let's continue for now. Okay, so that's just where we want to have the same material properties as above. So for ky, we are taking now the neighbors. It's in the x direction, but well, we take the neighbors themselves in the y direction, but we're averaging in the x direction in this particular case. And so for ky, we have one less row in this particular case. And so when we have the edge node for ky, at the top it doesn't really matter because we have the bottom one, so we just take the bottom nodes as references. So going back to multi-soil sheet, okay, oops, the multi-soil sheet, okay. So we are now calculating D3, so we now look at the upper neighbor times ky D3 again, and this guy plus D5 times ky d4. Okay, so again we skip 1 in this particular case. Okay, so we are not finished. We have to go we have to work on the bottom part of the equation, and the bottom part of our equation is given to us by this term here. So we have the delta x and delta y squared. Delta y squared goes to the sum of the kx's, and delta x squared goes with the sum of the ky's. Okay, so delta x squared will go with the sum of the ky's. So multiply that by the sum, so by the neighboring ky's. So ky d3 plus ky d5. Those were the neighboring ones. And then dy's go by the sum of the kx's. So that was kx c4 plus kx d4. Okay. Okay. So the x times the y, we have a weighted average. And at row 15 we have to eliminate everything up. Oh no, that goes up until here, right? Because here I had a slightly different formula. Yes. Okay. No matter. For now, we'll just paste over accepting the boundary condition. We don't want to overwrite them. Oops. We'll remove whatever is in this area. Which was our node. In our boundaries here, in terms of kx, so kx we go from qs, but we go q and q, and the same thing is r for and q. Okay, for kx. And we must copy that to the bottom here. Here we do the opposite. This becomes, so s becomes t, and the same thing for the other s, which becomes u, and this becomes t. Okay, now we're having a problem. So this is one of the messy things about these numbers. So let's yeah, the calculations don't want to proceed otherwise, right? So here we have to do the dx times ky. Ky has to be changed. So what was that? 13. I must go 15 and 14. Ky 13 becomes 14. Okay, so these numbers have been fixed. I will let's remove the neighbors. Okay. So we have a problem when something doesn't compute. Oh, that's a boundary condition, so we should recopy it. So using the iterations from inside the spreadsheet has its limitations sometimes. Okay, this is one of those cases where we hit a limitation. I'm not sure why we're having a problem there. Um, Okay, so why are these not recomputing? Ah, there. Okay. Okay, oops. Okay, so this is essentially to fix the number error that I had. Okay. So this is the general formula that I'm pasting everywhere here. Okay, so now pressing F9. Okay, there's obviously a mistake in the calculation somewhere. We don't seem to be converging to any sensible number right now. Lag is an issue, I'm not gonna lie. Let's save this. I'm just gonna close this for now. Try one last thing, if not we'll move on to the slides where I had obviously done the calculations before. I'm not sure what the mistake is here, but so if we disconnect it now, is the connection still very choppy? Okay. Let's try something else. See if I can open it with this one. Can you still hear me, by the way?
Yes,
Okay.
Yeah, Professor.
Is it less choppy now?
it's better than the
Okay.
rest of the screen.
Okay, so let's try if we can go. Oops. I think it's supposed to be this one. Okay, I need to figure out why calculations have converged to something that doesn't make sense. So let's save it as just as a numeric sheet. Okay. And just try to see if we can figure out. It's not showing. Spreadsheet. Okay, so what we are trying to do, oh, by the way, this is a little software called Numeric. It does lack many things. It doesn't have macro capability and so on, but one thing that is really good among spreadsheets, it has the best plotting abilities. So just to show you, so we could do, say, a matrix with the data we had last time, which looks a lot like what you would do with shading. Oops. And so we would define our data, define our x, y, and make sure that we define properly the okay. The y-axis should be inverted. Minimum set to 1 because that's the minimum value we have. So this is what it looks like. I mean, we can put axes, titles, and things like that. Increase the font size for the axis labels if we so desire. And things of that general nature. So that looks a lot like what we did last time. And we also have the nice contour line setup, which again we can do as we did before. So for the data, the Z data, we have it from here. The X values are here, and Y values and y-axis again, scale is inverted. And when we choose the style, we can define the axis color scheme. The scale setting again minimum at 1. And we can change also the major ticks, say 0.5 or 0.2. So it has very nice control. You can change your color scheme fairly easily. You can go to the pseudo axis, change colors. You can define new duplicate or edit and so on. Okay, so you can define a new map, change the number of colors that you're gonna have, and so you can make your own color maps if you want. Very easily, very powerful. I really like it for plotting. In terms of from all the spreadsheets, it probably has the best graphing utilities. Okay. Also, if you want to do a statistical analysis on spreadsheet, it's probably your best bet for a spreadsheet. So what we wanted to do here, and we seem to have had a problem. So I wanted to verify that we have correct values here, because I'm not sure what these have zeros everywhere. Right, these are constant values. This. So if I were to, let me try put 5 here. Okay, I'm just trying to figure out why this goes to 0.8. So there's definitely an error in the formulas. Because even when I force these values to be high, these go automatically low. So are we really far from what we had before? So we have dy squared times dkx d7 f d and f. Okay, that's the neighbors. And d and 7. Perhaps the boundaries. Kx, so dy times kx times some kx Anyways, I will leave it at that for now. We'll just look at what we should have obtained. I try to figure out where trying to solve things live can be a problem sometimes. Because you're trying to fix two things and think about the stream. So I'll leave it there for now, and we'll see. Because we basically used exactly this formula, which was working fantastically, and all we added was the neighbors. Right, so this one is the first one, so first one compared to the first one. C4 plus E4, D3 plus D5, C4 plus E4, D3 plus D5.
Professor, Excel sheet is not visible.
Oh, sorry. In terms of formulas, I think C4, D4, C. That should be D3, D4, not D5. Is that perhaps? And this one is T3 to T4. This one is also 14. Okay, that one. S. Okay, Y. Interesting. Anyways, I'll leave it for now, as I said. Let's move on to the next examples. But doing this previously, this is basically what I achieved in a spreadsheet. This is the kind of flow contour lines that you would expect to obtain as a result of these calculations. Okay. Live stream. Should I go to? Where is the? There you go. Oh. Okay, that should be it. Oops. Okay, so these are the contour line you should have gotten, and you can see the boundaries clearly, the boundaries of the soil layer. If you compare this to the previous shape, okay, where you have a homogeneous soil, once you introduce these boundaries, you can see them marked in the result, despite the fact that you have this transition in terms of your KYs. The little smudging there, this is what you end up having as a result. Okay, so chat window. So that being said, what we want to consider next is cases with where we have variable or transient problems, okay? Problems that will change over time. So basically, when we have steady state problems, we want to use them. So the steady state problem, like we saw before, we want to establish them for those cases. Oh, sorry, it's not showing. For those cases where there is no change of material properties over time, and that assumption can be good in many scenarios where you can reach an equilibrium and you can maintain it for a long time. But they're not always true, and sometimes we're interested in the time variability. So a lot of these problems will vary in terms of in terms of the pen with thin. There you go. Okay. So we have our rate of change of water content over time, which is, as we saw previously, we developed this already, is related to the change in to the second order change of head along the space, right? So in 3D we have the same general equation, and notice that this is the hydraulic head. When you express it in terms of pore pressure, you will have a difference of pore pressure in x, y direction as opposed to z direction, because you have gravity acting in the z direction, and you're trading elevation head for pressure head. Okay? And the hydraulic head is the sum of pressure head plus elevation head. So it does change the formulation a little bit when you express it in terms of pore water pressure. So the thing is, though, that you need to calculate water content. The hydraulic conductivity will become a function of the the hydraulic conductivity can be a function in these types of problems of the degree of saturation itself. So the water content, this is not a constant anymore, but it becomes a function of water content, right? So it's some function, so it's Ksat, basically. Is saturated hydraulic conductivity times some function that varies from 0 to 1 based on the water content or degree of saturation, however you want to express it. And so as you change this, it changes this, and that does make these calculations a little bit more complicated to evaluate. So to solve these problems, one thing that that you can do is first you need to realize that your problem is expressed in terms of its variability with time. Oops, this is the slide that I meant to have here. Okay. So basically, if you have d water content over dt, okay, and if you had that in terms of k, so this is assuming a constant k in space, not necessarily with water content, but you should distribute basically that k inside the so hi minus 1, okay, it's minus 0.5, minus 2, etc., etc. So you have to distribute it inside the equations the same way we did it today. But you have to notice that you have a term here that is the previous water content, which affects the following water content. So you now will have an evolution of water content over time. Okay. Again, the water content itself is related to hydraulic head. Okay, because the hydraulic content varies with metric suction, and metric suction is usually is defined as pore air pressure minus pore water pressure. Okay, and so when you have a given suction, you have a negative pore water pressure that becomes the value that you use there. So this suction value there is the negative of the pore water pressure when we are assuming that atmospheric pressure equals to 0. And so between each step, you basically have to recalculate the hydraulic head, because hydraulic head is equal to pressure head, elevation head plus pressure head, right? So from water content, you calculate pressure, and so they become fairly complicated to handle. That's why we're not necessarily going to be working on examples for these right now. I mean, this is something that you can definitely program, but it becomes a little bit cumbersome and error prone when we're trying to solve things on the spreadsheet as we have been doing. Okay. So you of course also have the Van Newton relationship. This is probably the one that is most commonly used in practice. And they're both really good relationships to relate the water content. So basically what you have is that your water content varies with suction, okay, in a curve that looks something like this. Okay, so you have tension saturation, and eventually you pass the air entry value, and the water leaves the pores relatively quickly until you get to residual water content, where water is reluctant to leave the pores upon further suction. However, we don't always have to worry about these complex relationships when we're considering transient flow problems. Okay, and actually 1D consolidation is one of those problems where we commonly use the fact that, or the transient flow properties. Okay, so we know what the flow rate of flow change is in porous media. This is how we developed our hydraulic conductivity equation, hydraulic flux equation. Okay. We also know that at steady state, the pressure head or the hydraulic head is the sum of the pressure head and the elevation head. Okay, so when you have a transient pressure, we have an excess pressure that we express here as HE. So that's the transient component of the pressure. At any given point, in our profile. So if we find the delta, the change in pressure between two neighboring points, we express this difference in pressure in terms of the existing pressure in the soil. Okay. In hydrostatic conditions, what we know is that the sum of HP plus Z at the 2 points is equal. So if I don't have so when things are hydrostatically constant, so the summation is equal. That means that if I have an aquifer, okay, so let's say that I have a clay layer here that separates two aquifers. Here the groundwater table is there. If I put a pipe anywhere in this aquifer, the water level will always go to this one. Say that I have a confined aquifer below the clay layer and the water level rises up to here. If I put a pipe deeper but still in the same aquifer, the water level will go to the same level in that pipe if they're hydrostatic conditions. Okay. And so what's left is the transient pressure. So if I have a transient element, that's what changes. So the change in transient pressure is basically equal to the change in pore water pressure. When in hydrostatic condition there's delta Z is equal, so it's common. So in hydrostatic condition, the only difference in pore pressure is the pore pressure itself, not the elevation is part of the hydrostatic condition. Okay, so the hydraulic head difference here of the is equal to the pore pressure divided by the unit weight of water, or the liquid in which I am calculating it. Usually it's water for our cases. So we know that the change in water content over T, over an element of T is equal to minus delta Q over delta Z. We saw that in the past. Now we're considering delta Z rather than delta X because we're considering specifically 1D consolidation. And so what we end up knowing about it is that the water content is, by definition, is the volume of water divided by the total volume. Okay, so that's one thing that we know from basic soil mechanics. And so what is the change in water content? The change in water content is equal to the change in water volume over total volume. And that's basically equal to the change in volume of voids. If we have a saturated soil, which is when we consider consolidation problems, usually we are assuming saturated soils, because if they're not saturated, what you will have first is compression of the air voids. Without that will be fairly rapid, okay, because typically if you have continuous air phase, you should have relatively speaking very fast evacuation of the air that is available to evacuate. And so what's left after that then is consolidation. Consolidation only starts once you have evacuated that air that moves much faster through the pores than the water does. Okay. And so basically that's equal to delta V over V, and that's equal to the volumetric strain, right? But if you consider only one-dimensional consolidation, that volumetric strain is the strain in one direction, so it's the same as the strain that you measure in an odometer. Now, one thing you have to remember if you have taken soil mechanics, you know that if you have any increase in total stress in your soil that causes consolidation, okay, so you cause consolidation by increasing total stress. You can also lower the groundwater table, but here we're considering the transient pressure increase. So if you load your soil with an increase in stress, instantaneously the total stress is completely transferred to the pore pressure, right? So that's what causes this consolidation problem. So the effective stress is not changing immediately, because effective stress is equal to total stress minus pore water pressure. So if I have an increase in total stress, so I'll call this condition 1, say effective stress 2 is equal to, so we have total stress 1 plus increase in total stress. So 2 is the change in effective stress immediately after loading. As I just said, immediately after loading, pore pressure carries all of the change in pore pressure is equal to the change in total stress. Okay, so basically that is equal to sigma 1 minus u1, okay, plus delta sigma minus delta sigma. And of course, that means that effective stress, so this is immediately after loading. Load. Okay. So because of this, we won't be seeing any immediate change in our effective stress. Everyone's okay with that so far? Everyone remembers that from undergrad?
Yeah.
Yeah? Okay. So then comes in the element of time in that case, right? But one thing, so we know that pore pressure change is equal to change in total stress. We also know that the deformation, the relationship between stress and strain for the soil is equal to the tangent modulus, M, which is basically it's basically Young's modulus, right? When you have Young's modulus, you plot stress versus strain. Okay, and of course in soils you don't have a straight line forever. You have a curve that looks more like that, and eventually it might even fall. So you can take your tangent modulus, means at any small increment, what is m? So m is not a constant, m is a function. Okay, so tangent modulus is basically a function of strain. Okay. And so you can define it like that, and of course the inverse is variation of strain over variation of stress. Okay. And we also said that the change in pore pressure is equal to the change in total stress, correct? So basically we can say that the inverse of the strain is, or the modulus, tangent modulus is equal to the change in strain over change in excess pore pressure. And so because, if you'll recall, we did say that change in stress, so basically change in water content is equal to change in strain. So what we can say is that we have the change in strain here is equal to d theta, and therefore d theta is equal 1 over m change in excess pore pressure, okay, in a saturated specimen, of course. So if we go back into our equation, we can replace d theta over dt by 1 over m times du over dt, and we say that that's equal to our Darcy flux. And of course Darcy flux is equal to, okay, our change in hydraulic head, but in hydrostatic condition the only changes in pressure that were in head are caused to pressure. So we go from dh to du, and we already saw why that was, right? So based on that, we have here the unit weight of water in the function, and what it comes down to is that we have the mechanical strain, so the modulus of the soil, how it compresses, its hydraulic conductivity at its initial void ratio, let's face it, that is a function also of the void ratio, and water content, okay? And that's basically what CV is, okay? So CV is basically hydraulic conductivity, that's the vertical, so that's why it's Z, times the modulus number, so the permeability of the soil, over gamma water. Okay, so we've just shown the formula that you have always known existed from Darcy's law, okay, and we've just derived how we can get to it just from thinking of it in terms of flow and in terms of stresses. Okay, so we attack our next sample. You want to take a little break? Pardon me?
Excuse me.
Yes?
You wrote all the formula with the assumption that they do not have any dissipation in poor water pressure. Am I correct, or
Well, we are going to have dissipation after this. So initially we don't have dissipation of pore pressure, it's instantaneously.
so when the poor water pressure dissipates, this formula does not apply?
Yes, it does apply.
Does
This
it?
is how we are going to calculate the dissipation of pore pressure.
Because in the first place you assume that all of the stress goes to the poor water pressure.
Yes, and now
But when
the change of pressure, yes, but then that's, so all the stress goes, so that tells us the maximum pore pressure, right? But there will be a change over time because we need to get to the steady state condition. Okay, so we know what the conditions will be at the boundaries, and see, this is the change of water content over time.
Oh, thank you.
Okay,
I understand.
so what causes the dissipation of pore pressure? So as we dissipate, so we're not initially we're not allowing. That's why we don't have initial dissipation of pore pressure, is that we're not allowing volume change. But later on, because of that strain, which is linked to the increase in stress, we allow strain, and so pore pressure will dissipate. Okay. We'll take a break and go into the example in 10 minutes after the break, if you don't mind. Okay. Hey everyone, we're back. Is everyone back on your side too?
Yeah.
Okay. Oh, you sound full of energy too. I can tell you recharge your batteries during the break. Okay, so, oops. Question from the example. So we have a uniform clay layer that is 8 meters deep, and it has a coefficient of consolidation of 1.10 meters square per year. Of course, that's not necessarily the units we use most of the time, but we use the units that are most convenient. It is subjected to a uniform stress increment of 10 kPa. So we're not worrying about stress changes over with depth, okay, in a profile. That's something we can add as an interesting additional complication, but right now we're not considering that in our calculations. And so the question then becomes, what is the degree of consolidation at the midpoint of the layer at the end of 15 years? Okay, so we want to do it at 2 meters intervals. We want to calculate the excess pore pressure at 2 meter intervals for the next 15 years. And we're going to assume dual drainage, okay, because it's 1D, so we do have to consider the type of drainage type at the extremities. So let's go ahead and work on that then. So we said that the change in pore pressure over time was equal to CV d square pressure over dz squared, right? And so if we take this and make it the difference equation, right? We assume that this time increments are constant, delta z is constant, and so we have here at any time u, we have I minus 1 minus 2 u I plus 1, right? And that's all at the same time value n. Equal at the central node. And at the central node, well, the delta u, well, first, let's just keep our delta u on this side. So we have delta u in time. So it's at the central node, so ui, okay? So we may want to calculate it at n plus 1 minus ui at time n, okay, over delta t. So we'll multiply by delta t, cv delta t over, sorry, that's delta z squared over delta z squared. Okay, so we have now established our basic equation. So to calculate our next pore pressure at time n plus 1, we can just isolate that term. And let's also convert this into a constant. We'll call it r. Okay. So this is equal to r times ui minus 1, no, all at time n, minus 2ui at time n also, plus ui plus 1 at time n, plus ui at time n. And so we can re-express this in terms, so it's r I minus 1 plus 1 minus 2. So this is 2r, right? Yeah, because we multiply r inside it, so this is 2r. 1 minus 2r times ui to the n, ui plus 1, okay, at time n. So that's basically the equation that we need to set for ourselves for all the various
Excuse me, ui plus 1 is r ui plus 1.
oh yes, I missed my r there, thank you so much. Oops. Okay. So that's the equation that we will need to evaluate our problem. Okay. And so we so if we move to let's open spreadsheet. Properties. Okay, so let us say we open a spreadsheet and want to solve the same problem. Oops. Okay. So what was the in the example? What was the value that we said? We have 8 meter deep. We want to go at 2 meter intervals next 15 years and 1.10 meters square per year. Okay, so 1.10 meters square per year after 15 years. Okay. So we want to go from 0 to 8 meters by increments of 2 meters depth, right? So we can definitely start by defining the oops, just I need to define a new box. Just a sec. Numeric dialog. So we define first our delta z. So I want to add a variable which will be delta z. Oops. And its value will be 2 meters. Okay, so if I say is equal to that plus delta z, and we go to 8 meters. I'm putting those horizontally for convenience, so that we can have time dependent variations vertically, where we have, it's easier to do new terms then. So we have these are the z values, the depth values that we are given, and so we want to calculate pore pressures at these depth values. We know that at time 0, so if I have time here, time 0, what is the excess pore water pressure that we have? We said it was 10 kPa uniformly over depth. So at time 0 I have 10 kPa uniformly distributed with depth. Okay, so that's the value that I will put here at all depths at time 0. Immediately after, I have pore pressures are equal to 10 kPa. Now I have to look in the time in the past, right? For time, so at the first time step, I want to know what my time increment will be. And now I have to go back to this term here. Okay. So remember this little equation? What we are working on now, it's called the explicit finite difference scheme. Okay. In the explicit scheme, we refer, so all the values known are known in the past, and so we always look backward to do to generate a trend that we extrapolate into the future. So when we do this, what we are doing, it's the easiest one to implement, and certainly on a spreadsheet it becomes super easy. You don't have to use a matrix, but if you're using MATLAB or Octave, you can still express it as a matrix operation to speed up your process, because MATLAB, Octave are optimized for matrix operations. So when you define them as matrix operations, you will actually go faster. But you don't have to do it in matrix. That's why it's so convenient to work on a spreadsheet with this. I mean, for our sake, we could even take a smaller delta z values, but I just want to show you something important here. If you want to have stable results, you should consider the values that you have here. Okay. So if I calculate R value now, so this CV is in what units meters square per year. Delta T is going to be in years. So we have millimeters square per year times year over meters squared. So basically that's it. R is dimensionless. Okay, important to note. So we want typically R to be less than 0.5, because what we want to is this term 1 minus 2R to be larger or equal to 0. Okay, for that to be the case, then 1 must be larger or equal to 2r, and so r must be smaller or equal to 1/2. Okay, that is a rule that we need to apply if we want a stable result from an explicit finite difference scheme. So once we have delta z established at 2 meters interval, we have CV, which is 1.10 meter squared per year. Then we know that R is smaller or equal to 1/2. Okay, which means that CV delta t over delta z squared must be smaller or equal to 1/2. And so delta t must be smaller or equal to delta z squared over 2 CV. Okay, and that will be in years in this case. So what's the time increment, the largest time increment that we can use? So we are limited in the size of our time increment. So 2 meters squared divided by 2 times 1.10, it gives us 1.81 years. That's the largest time increment that we can use. So what if we had used, instead of 2 meters, we had used 10 centimeters? Then the largest time increment we could have used was 0.004 years. Okay, so always be careful with this, and we will see what happens if we use a time increment larger than what we are allowed. Okay, but remember that is hard and fast rules to solve explicit finite difference problems. So if we take, we said 1.8 years, so let's take time intervals of 1 year. Okay, so what happens after 1 year? Or set up here for this sheet anyways. Let's add a new variable, call it delta t, and let's say that it's equal to 1 year. And can I define R in terms of sorry. So we're defining the various just defining variables here. CV, we said was 1.10. That's CV. What else did we want to define? R. And R is, what did we say R was? It was CV times delta t over delta z squared times delta, oops. Pardon me? You had a question?
A lot of disturbance in the voice.
I have trouble hearing what you're saying. Something about the Y's?
Yeah, Professor. There is some noise hindering your voice.
Some noise?
I don't hear any noise.
You're speaking very low. Am I low too? Is my voice high enough?
Yes.
Now it's good. Now it's good, Professor.
Okay, sorry. Um, so we have delta t over delta z squared. Let's make sure that that can be calculated. Oops. It might not allow me. I know. Okay, so we cannot have that value. We'll just have to calculate it on another sheet. Okay, so we'll calculate it here. R is equal to delta CV times delta t divided by delta z squared. Okay, so 0.275, and we will call that R in this particular case. Okay, so with the value of R defined here, so it's smaller than 0.5, so we're good. Okay, so always something you want to check. Now the boundaries are at 0 and at 8 meters, and what we know is that instantaneously after starting, the value will go to 0, right? Because that's what happens at the boundaries. Okay, when you have a soil under consolidation, the reason that you get these poor pressure distributions is because what you assume is that instantaneously after loading at the boundaries you get 0. Okay? And so technically we could say that even at time 0, at the boundaries, we're basically getting a value of a 0 in terms of poor water pressures. Okay, so they instantaneously drop down because those are boundary conditions that take over the initial condition. Okay, that's why I replace at my boundaries. So for the rest, the equation. Okay, so I replace at the boundaries. I replace my two values. And so what did we say the equation was for this? Well, we have r plus 1 minus r times the previous value. So we're looking at our previous values. Okay? So we're saying it's equal to r times the neighbor to the left at the previous value. So we're calculating for the next one. So at the previous value times the next, plus 1 minus 2 times r times at the same node but at the previous time step, plus r times at the next node in the space. Okay. Oops, we should have it 1. We have C4 plus 1 minus 2R that's 1 minus 2R. Oh, why is R defined as 0 now? Oh. Sheet 1, R. Oh, K1. no, the reference changed. Yeah, was that the? There you go. So we have now a proper definition of R. And so if we go at time steps, we want to go to 15 years, right? So we say that's previous plus the time step that we chose. We said it was 1 year. Okay, so we wanted at 15 years, what was the time dissipation at 4 meters, which was the middle of our layer. Okay, so we could choose to plot this obviously over time. So I could have at the depth. Alright, so we could plot it at different values of time. So after 1 year, after 5 years, after 10 years. Well, it's should be by rows. Forward. Let's make sure we define the series properly. X is C to G1, yes. Okay, so that's C to G1. The y's will be at 0. For this one, the y's will be at 1. This one, the y's will be at 5. Now we have, with the y's being at 10, right? 1, 0, 1, 5, 10, 0, 1, 5, 10, and finally 15. Okay, so if we insert this figure, okay, this is what we get, very squarish. Okay, now what would happen if I wanted to be a bit faster, and I said I want to use 2 years time increments? Okay, so if I want to use 2-year time increment, delta t, I change that to 2. Oh, that doesn't look right. Right, that's not a shape that it looks very very wrong, right? And if I were to increase that, it looks even worse. Okay, so the key here is that as soon as I went past 1.8, I went to a value of, I mean, this is not particularly good, so, but because of my geometry is very limited. But if I went to 0.5, say, okay, the shapes look much better. right? They look a lot more like the shapes that you're expecting. Of course, what you will say, well, what happens if we decrease, so we say 1 year still, if I decrease the size of my delta Z and I say that's 10 centimeters, again we get the R that is very small, very large, and so we need to find the delta T that is corresponding. So I think we said 0.00004. So let's not go that high. Let's make it 2.5. Okay. And then to find the delta T that corresponds to this, we said that we need a delta Z square over 2CV, right? So delta Z was 0.25 divided by 2 times 1.10. So we need 0.113 years. So if I multiply 0.113 times 12, so 1.3 months. So 0.113 times 365, so or 41 days. Okay. So the smallest time I could use is so if I go to 1/12 in that particular case, so 1 over 12, well, just one month, it's 0.0833. So 0.0833. So that corresponds to 1 month. I will just put the value next to it of time in months. Okay, so basically that is the time in months. Okay, very close to 1 month, 2 months, 3 months. So if we find the integer or round to 2 decimal places, it will still round off to nice value. So okay, so these are the values of time in months. And so we would get something very different in this case. Now the R is still too, oops, what? The R should have been okay. Did I not do it correctly? Let me have a look quickly at this. Live stream. Okay, so we said that we wanted to have oops, there you go. So CV is equal to delta T delta Z squared over 2CV. So I wanted to have where's my calculator? Okay. So we wanted to have CV was equal to delta t was equal to c delta z squared, so 0.25 squared divided by 2 times 1.1, oh, 0.024. So that's basically 10 days. Okay, so the largest time we can have is 10 days based on a quarter of a meter. And so if we do change that to 10 days or 0.0284 years, okay, so we go to Control F3. What we end up having is now we are at 0.5. Okay, that's nice. And we want to have so obviously this is no longer a boundary condition, so at that point we should continue having these values. And I will put them here so that so that's B2. I stop changing them every time. Okay, so these values obviously they stop changing at the edges, right? So we have here until we get to 8 meters. That's 4. Oops. 7.5, almost there. 8 meters. Perfect. And obviously we have to change all those values in the graph to AI. Gotcha. Okay, and that will be 0 at 8 meters because it's a boundary. So you saw what happened when we had the values that were not matching, and AJ 1 to so AI. And just changing the reference of my figures. Oops. Oh. Series 1. Ah. Okay, So the curves look much better when we are at the higher resolution like this, right? Now I also mentioned that you could actually do this in a matrix way, and if you were,
Excuse me,
yeah,
may I ask a question?
yes.
Mathematically speaking, why do negative values for 1 minus 2 are returned wrong answer?
Because it's more physically than mathematically. It means that, so the wave, the information travels at a certain speed through your medium. Okay, so because you have a given CV value, okay, that's that controls the speed at which information can move through your medium. And so you're looking at the past and predict the next step. And if you're within, so if the information has traveled less than your physical step, okay, you're still okay. But if you've moved, if with the given the speed of your of CV and the size of your medium, if you take a time step where it would require it to be beyond, you can no longer use the neighboring points to interpolate, okay? Because you're trying to interpolate something that will be much further. So it throws things completely out of kilt, okay? It has to do with that speed of information traveling through your medium. And it basically violates causality the same way that, you know, when you have the speed of light is the speed of light is c, not because it's not the speed of light, it's the speed of causality. Something cannot have a consequence faster than that speed. So that's basically the physical implication of that limitation. Okay, you're trying to go beyond. So again here, if I was trying to set a value of t, that was, so I will copy this, I'll just make it 0.05. Okay, this is what you're getting. You know, the information is just noise, okay, because you tried to go too far. So you're moving the information further than your delta z, okay, but you're using the neighbors, the immediate neighbors, to still average things out, right? However, in that amount of time, things would have gone way past that. So it's no longer valid to use the neighbors, okay, because the wave of information would have gone beyond. Does that make sense?
Yeah, we can say somehow the delta T and CV are related to each other.
Huh?
We can say CV and delta T are somehow related to each
Yes.
other.
Yes. And the delta z, because if you, the smaller you make for a given CV, for a constant CV, the smaller you make the interface, the smaller the amount of time you can afford to use. Otherwise, you're beyond your next node already. Okay, that's why they're related that way.
Yeah, thank you.
You're welcome. Um, so let's have a quick look at what it would look like if we were trying to solve things in matrix form. Okay. Oops. So if we're in matrix form, we have our formula, which was basically given by this. Okay. So let's say that you u0, the pore pressure at time 0, right? So that's at time n plus 1, right? That's what's supposed to be. So we were looking at different moments in time, and we want to have u at a given time, so u next is equal to something times u previous, right? So in this particular case, so let's see, at time 0, what do I have? I have 0, 10, 10, so that was at 0, 2, 4, 6, 8 meters, right? So 10 and 0. So at time equal 1 year, this one is 0, that one is 0, okay? It could have been a constant, it could have been 5, it could have been that value is, so we have to consider that. We're basically saying that that's equal to that, okay? And here we have from the previous time u0 plus 1 minus 2r u2 plus u, so plus u4, right, at the previous time. And so if you look at it this way, what we have is to calculate u naught up until u7, so so that will be at so u4, okay, so we have a vector here like this, which is equal to the previous one, again u3, u4, so u0 will always be equal to u0, so it's equal to the previous u0, and all the other values of pore pressure before that don't matter. u1 though is equal to u0 times r, right? So it's equal to r times u0 plus 1 minus 2r times u1 of the previous step plus r, and it's not affected by the other nodes. Then u2 is equal to r times u1 plus 1 minus 2r, so 1 minus 2r times u2, and r3 times u3, and 0 times u4, and u4 is equal to the previous u4 and nothing for the other ones, okay? So this is the matrix that I would use to multiply it by. So if I were to define, if I were to use MATLAB, Octave, I would define my matrix here, call it n, and I would define it as something like, of course you can use a little program to define these things, 0 comma 0 comma 0 comma 0 semicolon r 1 minus 2r r, and so on. So basically you're defining that matrix, and then you define your first vector at time 0, so you would define uprev, okay, as 0 what did we say? So semicolon, it was 0, 10, 10, 10, and 0. And then you could do your u next was equal to basically n times u prev, right? And then you could say u prev equal u next, and basically loop until you read. So that's how you would do these calculations on there. You can also do this here, obviously, where you could define a matrix n in terms of the number of nodes you have. So here I have increased the work size for myself. But what if I reduce it to something again a little bit more manageable? Let's say that I go back. Let's duplicate this. Duplicate. Okay. And let's say that for this sheet, which let's rename it to matrix. So if we rename it and I want to change again my delta z here, I'll go to the original value of 2 meters just to make things a little bit faster, and delta t to a value of 1. Okay. Obviously I need nothing after this, so okay, and at 8 we are at 0 basically. Okay, so we came back to the original simple formulation just to show you what we would get. So here I said that we would have a matrix where we had 1, 1, 2, 3, 4, right? And then
We're not seeing the X,
pardon me?
we're
Sorry, I
not seeing
can't
the
see
X.
your screen.
Oh, sorry. Okay, so I reduced the size of the table. I just duplicated the table. And then what we do with these is, so we establish it as a matrix, right? And so as a matrix, I have 1, and then I have R, 1 minus 2R, and R. I'll just put zeros everywhere for now. Okay, and so we can just copy and paste this. Oops. Oh, I have one row too many. Okay, and that's 1. So that's basically my matrix that, let me call it n. And so I could do now, if I wanted to get my my values. So let's repeat our little process here. Okay, where I have 10 all the way to 15 years. So let's repeat that here. We have our initial values at t0. Okay, and now because I have my vectors in horizontally, I will have to transpose, but I have m mult. Matrix 1 is n, and I want to transpose this this vector here, okay? And obviously I want to transpose the result, so it's again horizontal. Oh, sorry, did I use the, so it should be 24, not 4, 24. Okay. I will cut that, paste, and okay, so you see that I got exactly the same values as before, doing it this way. And it's just to show you how you would establish your matrix. Okay, so we did matrix operations. Values are a little bit rounded off a bit differently. Maybe I had has to do with the display only, but you can express it in terms of a matrix in the same way as we could. Okay, as we could do it with relative to nearby terms. So this is just what we did to solve that problem. And this is called the explicit difference method, because we calculate the future point looking at the past known points in the past. Okay, so we look backward to calculate this. Notice that we did a central difference for the in space. We were taking the nodes on both sides, not looking just at one side, but in terms of time we only looked at the past, so we did a simple backward difference. Okay. So another method that we can use is the implicit finite difference, and this one does require matrix operations, because now we express the known value in the past in terms of its neighbors in the future. Okay, those are obviously not known values, however. Okay, so when we're doing the implicit finite difference, we rewrite the equation in the same way that we did before, except that now everything is at n plus 1 in time, n plus 1 when we solve it. Okay, so we go from the same basic equation set. Okay, where we had delta u, but this time we say ui, so at time n plus 1 minus ui at time n over delta t, or let's skip this part, we already saw what this part was, right? So we can say that this is equal to r times ui minus 1 at time n plus 1 minus 2 ui time n plus 1 plus ui plus 1 at time n plus 1, right? So basically we want to find at I n plus 1, so we transfer everything on that side, right? So the known values is at time n, and so everything n plus 1 is unknown, so we have that's equal r times ui minus 1 n plus 1 minus 2r ui at time n plus 1 plus r ui plus 1 at times n plus 1. So here I say plus ui at time n on both sides. So what I end up having is minus r. So this goes on that side, that goes on that side. So everything becomes basically switch location and sign. So I have minus r times ui minus 1 at n plus 1 plus so we have 1 plus 2r, so 1 plus 2r ui at time n plus 1 minus r at time n plus 1 is equal to the known value I. Okay. And so here what we have is a matrix, if we express it here in terms of a matrix, which is, so for the first term, we're still looking at 1. And then we have minus 1, 1 plus 2r, so not minus 1 with minus r, 1 plus 2r minus r, minus 0, 0 minus r, 1 plus 2r minus r, and 0, 0, 0, 0, 1 times u unknown, next, is equal to u previous. Okay. So basically we have to find the inverse of this matrix. So call this matrix M, and now your u next is equal to times u previous. Okay, so that's how we evolve this next system. Okay. There's also another method that can be used, and in this particular case called the Crank-Nicholson. So you remember how in space we were taking the central difference? We were saying that the delta was based on the next two neighbors, right? We take the slope, which is a more precise way, like, of taking of measuring the variance. Okay, so imagine that you have a curve in space. So if you take this point and you look backward, you want to measure. You say you want to measure the slope at this point, right? So you look backward.
Excuse me, we cannot see what.
Oh, so did I change again? Sorry, I thought I had gone back to it. So if you go back backward in time, not necessarily in time, but so the straight line that joins these 2 points, ruler. Okay, so if we try to join these two with a straight line, right? That line does not really look like the slope that I can guess at this point, right? That looks like the slope at this point, but this line going backward, it definitely crosses it, right? Same thing if I take a point forward, it's not parallel to that. However, if I take 2 points equidistant backward, so backward and forward, same distance, okay, I end up with a slope that goes in the same general direction, much closer to the actual slope of the point of interest. So that's the reason why we were using the two neighbors around the center. But when we did with respect to time, we ended up only using one of them. So what's the alternative in that case? Well, the alternative is the Crank-Nicholson, where we are assuming that we're at a point in between two intervals. Okay? We assume that we want to take the value at a point between those two intervals, and therefore we have so we end up averaging the past. So that's why we have r over 2, because we say in terms of time we have un plus 1, and it is equal to the to r, but we say 1 over 2 because what we end up saying, okay, is you have I at time n plus 1 minus ui at time n is equal to r times the neighbors, but we want the average of the two neighbors, right? So we say 1/2 and then we add the 2 time steps. So we want half of ui plus 1 minus 2 ui plus ui minus 1. So 1/2 of that plus ui plus 1 minus 2 ui plus ui minus 1. So that one is at time n plus 1, n plus 1, n plus 1, and this one is at time n. So these are the known times, these are unknown, and we say that that time interval, that difference in the step, is equal to r times the average point. Okay? And so by doing this, we can rewrite it slightly. So we have r over 2. And for our purposes, I'll just call this rho, okay, for now. Okay, so r over 2 times basically ui plus 1 minus 2 ui plus ui minus 1. And these are all n plus 1, n plus 1, n plus 1. Okay, so if I say that rho equals r over 2, then what I end up having, if I keep all the time unknown on the left side and time knowns on the right side. So I'll distribute this. So n plus 1 will be there, rho times u minus 1, so it becomes minus rho ui. So that's, yeah, minus 1. Okay, to the power n plus 1. Minus, so plus 2, plus 1 plus 2 rho ui plus 1, I at time n plus 1, minus rho ui minus 1 at time n plus 1. And I transferred that one on the other side, so I end up having rho ui plus 1 plus 1, because this becomes plus 1 minus 2 ui minus 2r, 2 rho ui time n plus rho ui minus 1 at time n. Okay? So basically the matrix here will look the same as before, so 1 but we have minus rho, which is half of that what we had before. It's r over 2. 1 plus rho, 1 plus 2 rho, sorry, minus rho 0 minus rho 1 plus 2 rho 0 0 0 minus rho 1 plus 2 rho minus rho. Okay, so that's our first matrix times u next. And that's equal to r1 minus 2r, r plus 2r, r 0 0 r1 minus 2r, r 0 0 0 0 1 times u prev. Previous. So that's how we would encode them for matrix operations. Okay, and so if we call this matrix M star, because it's not R, it's rho, this one N star, then we have next is equal to minus 1 times matrix N star previous. Looks good. We're gonna finish there for today, but that's how you build these different matrices. Okay, so I'm sorry for taking, I think I went a little bit over time, sorry about that, but if you have questions, and next time we'll play on it, and I'll try to find the mistake that I made in the spreadsheet we did at the beginning of the class. It's probably something silly, so I'll try to find out where it is. Sometimes the problem comes from starting conditions, but anyways. Any questions?
No, thank you.
Oh, okay. So if you have no more questions, I'll let you go. Let you catch some Z's. Oh, yes, go ahead.
Um, I think I didn't follow the part. Why is it on the right hand side where it's R and not row?
We have rho because we were doing the averaging, right?
Okay.
So what we said was, okay, let's start at another value. So what we say, well, we have two sets of points in space, right? And so this is in space. And we also have, so two sets of points in time. So if I want to use Crank-Nicolson, I want to average out, but I want to assume that I'm in the position in time halfway between two steps, okay? So that the slope that I calculate is more precise to that point. Okay? So I say, well, the time that I want here is not really here or there. So what I'm doing is in time, I'm averaging out. So my change in time, so u at n plus 1, so my delta over delta time, so at different time steps over delta time, I want this to be averaged out. Okay, so the delta t here is constant, so it's going to go anyway into my value of r, right? So that's why I ended up having r. But because I'm averaging these two, so I'm saying it's the average of two time steps. So it's at time n plus 1, and this is at time n. So what's the average? Well, I have here my pressures at time n plus 1. So this is at I minus 1, I, and I plus 1. So I want my pore pressure at I minus 1, minus 2 ui. This is the same procedure we did the first time, so I'm not repeating. That's why I just write it down, but you remember it was the double delta, right? That's why we have 1 minus 2 plus 1 at I plus 1, okay? And these are all for future time at time n plus 1. So that's at time n plus 1. This is at time n plus 1. This is at time n plus 1, okay? So I'm multiplying this by these, obviously. But I want to add the previous time also. So I have the same three nodes. So it's exactly the same three nodes, but those are taken at time n. Okay. And now because I take the average, how do I find the average of two values? It's value 1 plus value 2 divided by 2. So I multiply that by 1/2. Okay. And that's how I have this 1/2 multiplying r that I call rho. Okay. Is because I'm taking the average. Okay. If I didn't divide by half, I would be doubling. So I have half the influence of the previous node and half the influence of the next node. And that's how I end up with ui n plus 1 minus ui is equal to rho, so at time n, rho ui minus 1 minus 2 rho plus rho. So does that answer the question? Hello, are you still there?
No, what I was asking is like in the towards the last end when you built the matrix, I was wondering why it was row and one side.
Oh, sorry, that was a mistake on my part. It's a that should have been rho.
Oh, okay. That's why I was
Okay, no,
asking.
that it's valid question. You should have asked it at that time. So at least yes, that's just a force of habit of writing R. Uh, I'm really sorry about that. That was confusing.
It's okay. I understand now.
Okay.
Yes.
Sorry about that. I'll see you next time then. Any more questions?